Welcome to Spring LIB.
Hi, let us imagine we have a rod which is fixed at 2 points A and B to a gear called D. I'm not showing a tooth because it's hard to draw. So this is gear D. Let me write this name somewhere else. Yeah, so let's call this point on gear D because we will need to calculate the velocity of point D. And then we have another gear here, C, and this point is fixed, and the length of AB is 120 millimeters, and the radius of this gear is 50 millimeters. Now, if the angular velocity of this gear is anti-clockwise, and let's call it omega naught, and omega naught is, I think it's 20 rotations per minute, 20 radians per second actually. So omega naught is 20 radians per second. Then what is the angular velocity of rod AB? Omega AB, let's call it. And we are also given that C is stationary. Okay, so as we discussed in the previous problems, at the point of contact, the velocity of the gears need to be equal. So to solve any of these problems, I always repeat, in each problem you need to break it up into translation and rotation. And for gear problems, at point of contact, velocities are equal. Okay, so let us look at this point where the gear is contacting point C. So if we draw the diagram here, so the velocity of this point here, so we have to break it into translation and rotational velocity. So the rotational velocity is going to point, if your omega is anti-clockwise, it's going to point in this direction. So, and the magnitude will be omega r, which will be, r is 50 millimeters. So this will be 20 times 50 is millimeters per second. So this will be 1000 millimeters per second, which will be 1 meter per second. Okay. Now, for this to remain stationary, this must have a translational velocity which is pointing in other direction. So let's call this point of contact point P. So this is the rotational velocity at point P, and translational velocity at point P must point in the other direction so that C is stationary. So since C is stationary, we get the translational velocity has to point in the other direction. So this is Vt, and all points have the same translational velocity Vt. For this is the definition of the rigid body. Okay, so we now know that since C is stationary, Vt has to be equal to omega r, and this will also be omega naught r. So this will also be 1 meters per second, which means this Vt is also 1 meters per second. Now we are required to find out velocity of AB as well. So A is fixed here, B is moving, and we have figured out that it's going to move down. So this is the velocity of point B, and since this is fixed, now if you are looking sitting at A, then this must be coming from the angular velocity. This component of velocity Vt must be coming from omega AB times L, the length of this rod, which is omega b r basically, since rotational velocity is omega r always, omega cross r. So this is going to point perpendicular because cross product is perpendicular to omega and r. This is our r vector from point A to point B. So it's perpendicular to r vector. Omega will be like this because we have figured out that Vt is going to be like this. So omega cross r will be just omega AB, which is not known, times the length of the rod. So this equation tells us that 1 meters per second equals omega AB times L, which is 120 millimeters. So this gives us omega AB as, let's write this down in millimeters as well. So it's 1000 millimeters divided by 120 millimeters per second. So millimeters cancel, and this is 50, this is 6. So this is basically 6, 8, or 6, 8 or 48, 2 remainders, then basically 0.3. So 8.33 radians, which are dimensionless, per second. This is omega AB. So this is omega AB. This implies. So we have figured out both omega AB, and what else was asked? Yeah, so omega AB was asked. So we have figured out omega AB, and velocity at point D is also something we need to figure out. So the other thing we need to figure out is what is the velocity at point D. So this is also simple. Once you know the omega, you know the omega. So velocity at point D. So this is point D. This will be translational plus rotational. So the rotational velocity, since omega is anti-clockwise, the rotational velocity at this point is going to point like this, omega cross r. So omega was 20 radians per second times 50 millimeter. So this is also going to be 1 meter per second. This is rotational velocity, plus now we have figured out the translational velocity Vt is 1 meter per second. So to this vector, so this was rotational part, this is going to be the translational part. So this, sorry, it's pointing down, not up. We have figured that out. So it's pointing down. This is Vt equals 1 meters per second. So these are rotational and translational components at point D. So velocity at point D is just this vector. So this is 1 meters per second, and then pointing down 1 meters per second. So this can be easily written as 1 I minus 1 J, or you can write this in terms of magnitude as well. So the magnitude, so this is the vector. Magnitude is going to be simply square root of 2, which is square root of 1 plus 1. And then the direction will be along the sum of these two. so somewhere along here. So root 2, and the units will be all meters per second, 45 degrees below horizontal. So we have figured out velocity at d as well. So remember, the basic principle is always the same. As long as you can break velocity into translational plus rotational, and you equate the velocity at the point of contact, velocities are equal. As long as you follow these rules, you will always be able to solve any such kind of problem. See you in the next problem.